Hi everyone, this is section 3.2. So we're moving on to whether a function can be linear or nonlinear. So now you know what a function is. You know that every x can only have one output, y, and that's what makes a function. So now we're going to find out whether a specific function is linear or nonlinear. So the first way we're going to look at this is with graphs. Does the graph represent a linear or nonlinear function? The word linear comes from the word line. So if you see a line in the graph, then yes, it is a linear function. So if you look at B is a linear function. A is this U shape. That is not a linear function. We'll learn about those later. They're called quadratics, but we're going to just write nonlinear. Now, try these problems on your own and then unpause the video to check your answer. The first one clearly looks like a line, so we can say that this is a linear function. And the second one, you might think, okay, I see two lines connected, but this is not linear. This is an absolute value function, which we won't learn about in this class, but that V shape is nonlinear. All right, these problems require you to find out if a function is linear or nonlinear based off of a table. So on a table, you need to understand that the key word here in definition you're going to need to look for is a constant rate of change. And that means that the difference in the y over the difference in the x's is the same for each coordinate. And we'll go over that in a moment. So you can think change in change in y divided by the change in x, and that's just the difference if you subtract coordinates, which you'll see in a moment. So the first one, we look at the change in the x. How do you get from 3 to 6? We add 3, and it's pretty constant throughout the whole table. And we want to do the same thing for the y's. For the y's, 36 to 30, subtract 6. For the next one, 30 to 24, subtract 6, and the last one is subtract 6. Since these are all the same and these are all the same, I know for a fact that there is a constant rate of change, and therefore it is a linear function. That's all you need for the explanation. Now, if I ask you what the constant rate of change is, what you do is you divide the change in the y's divided by the change in the x's. And if I did that, I know the symbol looks a little crazy, but it's really just dividing -6 by 3, which is equal to -2. That's the rate of change, and it is constant throughout the whole graph, throughout the whole table. All right. For part B, try finding the change in x's and the change in y's, and then play the video to check. All right, so you should have gotten different values for the change in the y. Now, we know that this is nonlinear because they're not constant numbers each time. Here they were, but not for the y's. So it's nonlinear, no constant rate of change. Now, I can still say there's a rate of change between some of the coordinates. Whoopsies. And if I asked you specifically what's the rate of change between 1, 2, and 3, 9, you would just say that's okay, that's 7 over 2. Change in y over change in x. It would be 7 over 2. We don't need that piece of information. Try these table problems also on your own. All right, so for this problem, if you look at the change in x's, they were consistent in both problems. Let's look at number 3's change in y's. They are each 2, and therefore, yes, this is a linear function. Again, if I asked you the rate of change, it would simply be the y change over the x change, so 2 over 1, which is equal to 2. You don't need this part in this problem, but it's good to see it, especially if you need to explain. You're like, okay, this is a constant rate of change. and you need to write that as your explanation. You don't need the number per se, but to find it might help you, like it's 2 over 1 for each of these. That means it's constant. In the second one, notice we have a -4, a -4, and a -2. If I were to set those fractions up, we'd have -4 over 1, -4 over 1, -2 over 1. They're different, so therefore this is nonlinear. And the reason it is nonlinear is because there is no constant rate of change. All right, the following problems you need to identify if it's a linear or a nonlinear function just by looking at the equations. You guys have a graphing calculator, so I'm going to show you both ways to think of it as to look at the problems with a calculator and without. So let's do the first one with a calculator. Oopsies, it's not a highlighter. Y equals 3.8. So let's do that. Go to y equals, type in your equation, y equals 3.8, hit the graph button, and there you have your graph. It's a line. So now I'm going to say that this one's linear. How about the next one? 2, y equals the square root of x. When I go to my calculator, hit y equals, type in the square root, so that's second, and this button, oops, wrong one. Second, x squared, and then you're going to type in x graph, and that's also not linear. So put nonlinear. All right, so now just looking for things that automatically tell you something is nonlinear without even having to graph it. So looking in the exponents, there should be nothing in your exponents. So here I have an x. That should not be there. So anytime you have a variable in the exponent, it is definitely nonlinear. Anytime you have a variable in a denominator, we know it is nonlinear. Anytime the power of x is anything other than 1, it is nonlinear. Anything in the form of a y equals a number, or y equals a number times x, or y equals a number times x plus another constant, this is called slope-intercept form, we'll learn about it later, that's always linear. So here if I were to distribute this, you don't have to, but we have y equals a number x minus 6, and that's definitely linear. Again, you can always graph these and just look at the graph to see if it is in the shape of a line and go from there. So if it's a line, it's linear. If it's not a line, it is nonlinear, and that's it. Now when you explain these, you can talk about the graph, the shape of the graph. So you could say it's a line in the graph, or it's a curve. Or if you want to talk about what you're seeing, there is a 2 in the exponent. So exactly why you think it's nonlinear, write that down. All right, last thing is the difference between discrete and continuous. So we did this a little bit in the last video, but we didn't define it. So discrete domain, it's a set of input values that consists of only certain numbers in an interval. So 1, 2, 3, 4, 5. Those were the graphs you saw as separated points. There were specific points. There was nothing in between, which you would get when you have a continuous function. So a continuous domain is a set of input values that consist of all numbers on the interval. So if we talk about all of the numbers 1 through 5, there's an infinite amount of numbers there. Even between, let's talk about 0 and 1. There's an infinite amount of numbers between 0 and 1. I could say 2.000, that's not even between 0 and 1. I can say 0.0000009 and just keep adding zeros forever and ever. So there's an infinite amount of numbers between 0 and 1, which is why we use inequalities when we talk about the domains of continuous functions. Versus in a discrete function, I can just list it. 1, 2, 3, ... whatever they are. Right?